Matt Whalen coming to you virtually from the Lightstage lab at Google LA. From 2017 to 2024, this was my home away from home where I helped develop camera and lighting electronic hardware to enable research in augmented and virtual reality. The Lightstage itself is the brainchild of Paul Debevic, a good friend and a pioneer in virtual effects, who worked on many groundbreaking movies like Avatar and Benjamin Button. The Lightstage sphere behind me had an array of over 100 high-resolution cameras operating in both the visible and infrared parts of the spectrum. It also had an array of over 300 custom LED-based lighting modules that could reproduce practically any lighting environment you could imagine, from an outdoor scene on a sunny day to the inside of a cathedral with sunlight streaming in through stained glass windows. So, by taking a whole body scan of someone standing inside the sphere, you could create a digital representation of a person that could be inserted into any type of lighting environment. A great video that demonstrates how this Lightstage works is the Relightable at the web address I've shown below. In it, you'll see a clip of yours truly that shows why I chose a career in electronics rather than as a circus juggler. For those of you who want to nerd out on the details of the Lightstage, the clip that follows should satisfy the nerdiest. In this section, we'll be discussing the construction and hardware design of the Lightstage. For some historical context, the Lightstage system at Google and other similar installations worldwide are derived from the pioneering research and development efforts of Paul Debevic, Zhuming Yu, and the team at the Institute for Creative Technologies at USC. At Google, we have built on this foundation to create a versatile and powerful tool for image-based modeling and reconstruction. Our talk covers two main hardware areas: the mechanical design and construction of the stage, presented by Jay Bush, and the electronic design and construction of the illumination system and the control electronics. At this point, I'll hand it off to Jay.
The Lightstage X series structures are designed after a V3 icosahedron of varying diameters. With this geometric shape in mind, a custom algorithm is run to generate the unique rough pieces to construct the skeletal frame of the stage itself. Using these mathematically generated pieces, mechanical drawings are then created for manufacturing. Many mechanical drawings. To ensure rigidity, the stage was designed to use a dual star vertex system. Reasoning behind this is because with only a single layer, it allows bending between the struts and the joints of the structure. With the dual system, the only way for an internal joint to bend would be to stretch the exterior metal star, and the shearing strength of metal is much stronger than the bend strength. An additional benefit of using a V3 icosahedron shape is that it can be broken into 10 equal slices, one of which is used for the door. To keep the system clean, these slices are used to isolate clusters of lights for equal distribution of power. Each slice hosts a single power hub that supplies a measured amount of power to each light mounted to its quadrant. Multiple lengths of wire are then run through the structure's struts to each light, keeping the power wires neatly managed and out of the way. In addition, this also allows for the stage to be assembled and disassembled with minimal fuss to the power network itself.
Thanks, Jay. I'd just like to add that not only was Jay instrumental in the design of the Lightstage, she pretty much built the entire structure at Google by herself. This Lightstage is so well constructed that I like to say that if there's ever a major earthquake in LA, I hope I'm standing in the Lightstage when it happens. Now let's talk about the Lightstage electronics. I'll be describing this with a bottom-up approach, starting from the individual LED components and progressing upward to how the entire illuminant array is designed and controlled. One of the most critical components in a light stage are the light sources used for illumination. The advent of small, high-power LEDs has enabled a wide variety of illuminant options. Our design goals for this stage were to combine high optical power and broad spectral coverage in as small a form factor as possible. Based on color science research of Chloe Legendre at USC, we also realized the need to supplement the standard RGB LED spectral coverage with a mix of other colors to more accurately render scenes. The Philips Luxeon Z series of LEDs best fit our criteria for output power and small form factor. For example, the output of a single cool white LED was about 1/3 as bright as a 60-watt incandescent bulb in a much smaller package. In addition, the Luxeon Z series offer a wide variety of output spectra, as you can see from the graphs. In the end, we chose 7 different color LEDs: white, red, green, blue, amber, lime, and royal blue. These gave us spectral illuminant coverage over the visible range and maximized the color gamut available for image capture. Our goal at the outset of this project was to enable both high-resolution face and body scans to be done in the same stage. To this end, 2 sets of LED clusters were designed for each light source on the stage. One set of LEDs were used with weak focusing optics to provide a uniform bright illumination at 1.75 meters, the radius of the light stage sphere. This is shown in the red triangles in the figure, and it was intended to illuminate the face and shoulders of a person standing in the center of the stage. The second set of LEDs were used without optics and output a roughly Lambertian intensity pattern. These were intended for whole body illumination, as shown by the yellow triangles in the figure. The physical layout of the 2 groups of LEDs is shown in this slide. The outer ring contains the face scanning LEDs in a cluster of 26 devices: 6 white, 8 red, 6 green, and 6 royal blue. Provisions were also made to attach polarizing filters to specific groups in the ring to enable polarization-based image analysis. The inner group contained 37 LEDs in a tight cluster, including 11 white LED sources. The size and placement of these devices were such that from the center of the stage, they approximated the size of the solar disk as seen by eye. Because of the amount of current drawn by these devices, thermal management was incorporated on the printed circuit board in the form of a metal finned heatsink and cooling fan. Each LED printed circuit board was comprised of 3 main functional sections: power management, control logic, and LED drive electronics. In the power management section, 2 power management ICs were used to convert the main light stage bus 24-volt input into the LED driving voltages and logic voltages needed for control. The control logic section consisted of a mid-scale FPGA that managed I/O with external devices, controlled LED pattern sequencing, and gated the LED outputs. The clusters of LEDs were addressable from the FPGA in a 20-bit bank. LED patterns could be loaded manually via a programming port or from a master control board via the host I/O port. A scan sequence was triggered externally from a master device by outputting short pulse trigger signals common to all boards. LED pattern sequences could be stored either in a non-volatile ROM or dynamically in DDRAM. The LED driving circuits used both a coarse analog current control via digital potentiometer and a fine-tunable pulse density modulation scheme to provide stable linear LED output levels. The LED boards were assembled onto the light stage in a daisy-chained array of 311 printed circuit boards. This slide shows how complex light patterns could be produced from a single master trigger device. In creating a light stage pattern, each LED PCB was programmed with a unique sequence of LED drive patterns. These patterns were determined algorithmically and were dependent on each board's geometrical position on the light stage. With these patterns stored in the LED ROM, a master trigger signal could be transmitted to the stage that would cause each board to step consecutively through ROM locations and cause the appropriate LEDs to light up. The ROM had sufficient storage to hold thousands of static patterns or complex time-varying patterns. This slide shows the hardware architecture of the full Lightstage illumination, depth sensing, and image capture systems. A master controller transmits coordinated sets of trigger pulses, one to the LED array and one to the image capture and depth sensing pods. The image capture system is a large array of 12 megapixel color machine vision cameras capable of capturing data at high frame rates and storing the data via multiple PCIe interfaces on image server PCs. Depending on the requirements of the scan, either narrow field of view front-facing high-resolution cameras can be used, typical of face scans, or wider field of view for body capture scans. The depth pods are comprised of an IR pattern projector and IR filter monochrome cameras placed evenly around the stage. The operational modes of the stage listed here highlight the versatility of this system. Lighting patterns and image capture modes include one light at a time, color gradient for both body and face, spherical harmonic light patterns, and complex static patterns for lighting reproduction. For all of the nerds out there that made it to the end of this presentation, congratulations! And happy holidays from this old fart to all the old farts talking tech out there. See you in 2026.